Hey everyone, and welcome to This Explainer. Today we're going to completely demystify one of the strangest, most absolutely fascinating things in existence. We're using some incredible source material to unravel cosmic objects that, honestly, just don't seem to make any sense at all. But stick with me, because by the end of our time together, you're going to see exactly how they work. So, what actually happens if you fall into a black hole? I mean, it's kind of the ultimate mind-bending cosmic question, isn't it? But to answer it properly, we can't just look at the physics from afar. We really have to take a complete experiential journey into the dark. Okay, let's just jump right in. Here's our roadmap for today. We're covering 1. The violent birth, 2. Anatomy of the abyss, 3. Crossing the event horizon, 4. Monsters of the cosmos, and finally, 5. The final evaporation. We're going over the whole shebang, from a star's dramatic collapse all the way to the very end of time itself. Part 1. The violent birth. Because ironically enough, the birth of a black hole actually kicks off with a spectacular death, specifically the death of a supermassive star. Now, as you probably know, stars are essentially just massive collections of mostly hydrogen gas. Deep in their cores, nuclear fusion is constantly crushing that hydrogen into helium, which releases this tremendous amount of outward energy. And that energy perfectly balances the inward crushing pull of gravity. But extremely heavy stars, they keep fusing heavier and heavier elements until they hit iron. And that is absolutely crucial, because fusing iron doesn't generate energy. So the iron builds up, that delicate balance is completely shattered, and the core collapses in literally a fraction of a second. It implodes at 1/4 the speed of light, triggers a massive supernova, and, well, what's left behind is a black hole. Moving on to part 2, anatomy of the abyss. So, what exactly is the structure of this thing that's left behind? Let's break down the black from the whole. Starting with the black part. This is the event horizon. It's a completely black spherical boundary that reflects absolutely nothing. And the reason it's totally black is because the gravitational pull is so wildly intense that anything crossing this boundary would need to travel faster than the speed of light just to escape. And since we know that's impossible in our universe, nothing gets out, period. So all we see is a perfectly black sphere. Okay, so if the event horizon is the black part, what's the whole part? That would be the singularity. Now, science isn't entirely sure what this is exactly, but our source material describes it in a way that just hits the nail on the head. It's thought to be an infinitely dense point where all mass is concentrated with absolutely no surface or volume. You can think of it like a cosmic dividing by zero error. It's this core where our current understanding of reality basically just throws its hands up and breaks down. Real quick, before we go any further, I want to shatter a super common myth. Black holes are not vacuum cleaners. They don't just roam the galaxy indiscriminately sucking up planets. If we magically swapped out our sun right now for a black hole of the exact same mass, Earth wouldn't get sucked in. Our orbital path would actually stay exactly the same. Though, just to inject a bit of morbid reality here, we would absolutely all freeze to death without the sun's heat. So there's that. Part 3. Crossing the event horizon. Mechanics aside, let's make this personal. What would actually happen to you if you crossed that dark threshold? The very first thing you'd experience is just mind-boggling. We're talking severe time dilation. Gravity warps time, right? So from the perspective of an outside observer, say you have a friend safely watching you from a spaceship, they would see you visibly slow down as you get closer to the event horizon. To them, you'd basically freeze in time, slowly turn red, and then just fade out. But from your perspective, looking back out at the universe, you would watch the rest of the cosmos hit the fast-forward button. You'd literally be watching the future unfold. Now, once you actually cross the horizon, physics gets pretty fuzzy, but scientists have 2 leading theories for how you'd ultimately meet your end in there. Option 1 is spaghettification, and option 2 is the firewall. They're both equally horrific, but honestly, super fascinating to think about. Let's look at spaghettification first. Inside the event horizon, space is so heavily curved, it acts kind of like a super tight alleyway that instantly closes behind you with every single step. You can only move in one direction, and that's inward. And because the mass of the black hole is so incredibly concentrated, a distance of just a few centimeters means gravity is pulling with millions of times more force on different parts of your body. So your feet are being pulled millions of times harder than your head. The result? Your body stretches and stretches until your cells are literally torn apart, and you become a hot stream of plasma exactly 1 atom wide. The other theory, the firewall, just suggests you'd hit a massive wall of energy right at the horizon and be incinerated instantly. So yeah, definitely a rough way to go either way. Section 4, Monsters of the Cosmos. Let's zoom out for a second and look at the sheer terrifying scale of these objects. I mean, how big do they actually get? The contrast we're looking at here is just staggering. On one side, we have stellar mass black holes. These are relatively tiny, maybe just a few times the mass of our sun, and they have the physical diameter of like an asteroid. But on the flip side, we have the supermassive black holes. These are the ancient cosmic titans sitting at the heart of pretty much every galaxy, and they've been actively feeding on stars and gas for billions of years. Just let this number sink in for a second. 40 billion. That's 40 billion times the mass of our sun. That is the amount of mass crammed into the largest known supermassive black hole, this absolute behemoth called S50014 plus 81. And to put that absolute monster into perspective, S50014 plus 81 has a diameter of 236.7 billion kilometers. That is literally 47 times the distance from our sun all the way out to Pluto. It's so incomprehensibly huge that, as a general rule of thumb, the further away you are from the singularity, the longer you live. So if you happen to fall into this specific monster, you could actually just sort of hang out and travel inside it for quite a while before you finally died. Which brings us to part 5, the final evaporation. Because as powerful and immortal as these cosmic monsters seem to be, they actually don't last forever. Even black holes die eventually. Their death comes by way of a really slow process known as Hawking radiation. You see, empty space in the universe isn't actually empty. It's constantly bubbling with these virtual particles that pop into existence and then immediately annihilate each other. But when this little pop happens right on the absolute razor's edge of a black hole's event horizon, one of those virtual particles gets sucked in and the other one actually escapes and becomes a real particle. The kicker here is that the escaping particle essentially steals a tiny fraction of the black hole's energy. At first, this drain is agonizingly slow, but as the black hole starts to shrink, the whole process just accelerates. And this evaporation operates on this crazy accelerating timeline. Once a black hole has finally shrunk down to about the mass of a large asteroid, it's radiating energy at roughly room temperature. When it shrinks even more, down to the mass of a mountain, it starts radiating with the intense heat of our sun. And in that very last second of its life, it completely evaporates, exploding outward with the unimaginable energy of billions of nuclear bombs. But how long does that whole agonizingly slow evaporation process actually take? Well, for the largest supermassive black holes out there, we're talking about 1 Google years. That is a 1 followed by 100 zeros. It's a span of time so ridiculously massive that our human brains literally can't even visualize it. Which leaves us with this final, really lingering thought from the source material. By the time that 1 Google years passes and the very last massive black hole finally flashes out of existence in a nuclear explosion, nobody will be around to witness it. The universe is going to be completely uninhabitable long, long before then. It's this humbling, almost provocative reminder of the sheer, quiet scale of cosmic time and exactly where we fit into the grand life cycle of the universe. So, what do you think our cosmos will actually look like when that final explosion happens? I'll leave you to think on that.